Hello, my calculus kiddos. Welcome back for another exciting lesson in calculus. Today, we are starting our new unit. This is Unit 2, and the focus of this unit actually picks up right where we left off in the last unit, when I introduced the idea about the instantaneous rate of change, or in other words, the slope of the tangent line. The whole purpose of this unit is to define that a little bit further and figure out ways to make it quicker to determine the slope of a tangent line. Now, it may seem simple, it may seem like, well, okay, why are we focusing so much on the tangent line? But we'll see as time progresses how that applies to so many different things in life, okay? Specifically particle motion, any types of rate of change of any kind will be understood at a much deeper level once we get through the idea of the derivative. Okay, and that's the title of today's lesson, the derivative. And our goal here is to understand what a derivative function is and how to determine it in some basic cases. Okay, first of all, the derivative is the slope of a tangent line at a given point or at a certain point. Okay, the slope of a tangent line to a curve at a given point is referred to as the derivative of the function at that point. And you might say, well, how is that any different than what we've been talking about before? There is no difference. We just have a name for it now. Okay? So we have a curve. If I find the slope of the tangent line at that point, that is the derivative at that point. Obviously, the slope at this point, if I draw the tangent line there, you can see that the slope is going to be different here versus at any point along the curve, right? The slope changes depending on where we are on that curve, okay? Another way to say the slope of the tangent line, it's just the slope of the curve at that point, okay? The curve has a slope to it, and we can see it, I think, pretty easily. We would say, okay, this is pretty steep as we start out, and then it starts to flatten out. And then it gets to go steep again. The point is the steepness is changing. The slope is changing. So there is a slope to curves, but the slope is different at each point. And that's the idea of the derivative. The derivative is the slope at given points along that curve. Okay? Now, we refer to it, there's different ways of saying the derivative or different applications of the derivative. One of them is the slope of the tangent line, obviously. Okay. Another thing we call it is the instantaneous rate of change. Now, moving forward from here on out, if I just say rate of change, I don't use the word instantaneous, but I say what's the rate, that implies the instantaneous rate. Okay. If I say rate, I mean the rate or the slope at that particular point, not the average rate over a time. Okay. The slope of the tangent line, the instantaneous rate of change, are different ways of saying the derivative, but we use the term derivative to represent all of those things, or both of those things, and a lot of other things later on. It's written in a lot of different ways, okay? Y prime is what we say here. Y with a little, notation there is Y prime. We've used that notation in transformations when we move from one triangle maybe to a different triangle on a graph, but here it means something different. Y prime is the derivative of y, okay? Another way of saying that, if we're in function notation, is f prime of x. F prime of x, right? The little apostrophe is prime, all right? Another way of saying it is dy dx. You go, what in the world is that? Well, first of all, we say it this way. We say the derivative of y with respect to x. The derivative, let me highlight this here. We're saying the derivative of y in respect to x. Okay, so this is y prime. The derivative, that's lowercase delta, but we can say derivative of y in respect to x. All right, another way of writing it is df dx. The derivative of the function f in respect to x. The derivative of the function f with respect to x. And then another way, last way of saying it, is d dx of f of x. Now I'm going to tell you right now that when I was in high school, I really liked the the first two notations, the y prime and the f prime. It was just simple, it was clean. I did not feel comfortable with the dy dx and everything below that, and here's why. Okay, the first two notations are how Isaac Newton, this is how he wrote the derivative. Okay, but we also have another guy named Leibniz, and both of these guys kind of discovered /developed calculus about the same time in history, and they kind of discovered them separate of each other. Neither one of them knew that the other one was basically doing the same thing. But Newton kind of looked at it from one angle, and Leibniz kind of looked at it from a different angle, and we'll talk about more of those angles in the future. But Newton had a simplified notation. The problem with Newton's notation is it didn't explain what was taking place. Leibniz notation really helps us understand what's going on. And so I'm going to give you that because it's really going to help you develop your understanding of calculus if you understand it in Leibniz form, and then obviously you can use the simpler form on your own, but you really need to understand this. So let's say we have a curve like this, and I'm gonna change the direction just to keep it simple. Okay, let's say we have a curve that looks like this, and I want to find the slope at any given point. Well, we know that the slope of the tangent line, or the slope of the curve, or the derivative, we'd say, the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? Now remember slope, just the general idea of slope. Slope is the change in y over the change in x. The change in y over the change in x. So if I were to ask you to find the slope between these 2 points, the average rate of change between these 2 points, what you would do is, in a sense, you could draw a secant line if you want, but then you would draw a triangle. And this represents your change in y, this represents your change in x. And so the slope between those 2 points is change in y over change in x. But when we're talking about the derivative, we're talking about looking at the slope at a singular point. So what we do is we move this point closer and closer and closer to this point. And so let's say instead of looking at this big change, let's move that point a little bit closer. So let's move it here. Well, we would draw our little triangle here. This would be my change in y over change in x. And I move it closer and closer and closer. The bottom line is you can look at it this way. This is the capital letter delta, right? Capital letter delta. The derivative is written as, let me cancel this out, dy dx like this. This is the lowercase delta. So when we're looking at the average rate of change, we are looking for the big change in y over the big change in x. But when we're looking for the derivative, we're looking for a very small change in y versus a very small change in x. That's why we use the lowercase delta instead of the capital delta. So these points are infinitely close, so we use the lowercase delta to represent the small change, okay? So that's one way of looking at it. And then obviously you can replace the y with f as well, because I have function notation here. Now, I want to point this out because I think the last thing might look a little confusing. If I say d dx of y, like this, what this actually is that this is a noun, this is the subject, okay? And then this is the action, this is the verb. This is telling us to do something upon that noun. It's telling us take the derivative of the subject in respect to x. And we'll talk more about the in respect part later, but take the derivative of y in respect to x. And mathematically, you can view it this way. Well, that would be equivalent to dy dx. And so that becomes a noun. If you take the derivative of y, you get the derivative, essentially. Okay, so this is now a noun, a result. Okay, so those are just different ways of notating the derivative. The slope of the tangent line, the slope of the curve at a given point, or the instantaneous rate of change. We can use any one of those notations, but the simplest form is obviously y prime and f prime of x, okay? The derivative of f at x. Now, The definition, I had it up here a second ago, the definition of the derivative is exactly what we've seen before. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now remember the bottom, I actually had this before for the bottom. I had x plus h minus x, but every single time the x is reduced and you're left with h. That's why I just put the h there. So, but still, the bottom line is, let me write it out. This is the y2 minus y1 over x2 minus x1. It's still the slope. It's the change in y over the change in x, but it's the small change. And the reason it's the small change is because we're taking the limit as h approaches 0, which means these 2 points, these 2 x values are converging. They're getting closer to each other, essentially, or one of them is getting closer to the other, I should say, okay? And then we would say if the limit exists. If the limit does not exist, we have other issues. We'll talk about that later on. But here's the diagram, and we've seen this multiple times. Okay, if this is x, and this is x plus h, because it's h units away from x, and then this coordinate would be f of x comma f of x, and then this coordinate here is going to be x plus h comma f of x plus h. And then we just find the slope between those 2 points, essentially. That's a change in y over change in x. But we are moving this point closer and closer and closer to our x value, which means these heights and this height and this width, or this change in y over change in x, become small values. That's why we use delta y over delta x, lowercase. And that's why we take the limit, okay? Now, an alternate definition is this. F prime of x is equal to the limit as x approaches a of f of x minus f of a over x minus a. So I'm going to take a second to kind of develop this guy. This is one type of definition, or one definition of it. The other definition is that f prime of x is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Well, you can still see the slope formula in here. There's your y2, y1, x2, x1. We're essentially, though, now we're taking the x and approaching a. So graphically, here's what it looks like. We have, in this case, we have coordinate a comma f of a and coordinate x comma f of x. And what we're doing is we're moving x closer to a. So as an example of this would be something like this. We would say that this is coordinate a and this is x. And let's say the curve maybe looks something like this. Okay, there's our 2 points. Okay, what we're doing is finding the slope of that secant line, but we are moving x closer and closer to a. As x gets closer and closer to a, this point moves further and further, or closer and closer to the other point. And so when we find the slope there, the slope formula is y2 minus y1 over x2 minus x1, but we're just taking it so that the x value is approaching a, so it becomes, again, a very small change in x, very small change in y over the very small change in x. So that's another way of seeing the definition of the derivative. Now, I know some of you are going to go, I don't even want to deal with that. I want to deal with the other one because that's what I'm comfortable with at this point. But I'm going to tell you right now, this is more direct in terms of seeing it. I see the slope formula there, and I don't have to really go too far into understanding it. I'm moving x closer and closer to a. As I do so, it almost becomes that point, and as a result, f of x is getting closer and closer to f of a, and I'm just finding the slope between those two, okay? So again, there's x, there's a. I actually have it backwards here, but that's okay. In this case, we would just be moving x this way. X is approaching a from the left instead of the right. So delta y over delta x, but the small change, right? Notice these graphs are of secant lines. We're looking for the graph, the slope of the tangent line. And so we only get the derivative, we only get the slope of the tangent line when we throw in the limit statements. If we ignore the limit statement, all we're doing is finding the slope between 2 points. The limit statement is the thing that makes it infinitely close to the first point, which tells us it's the slope of the tangent line at that point. All right? So let's go ahead and take a look at an example here. And I'm going to show you, or I think I'm going to attempt to show you, both ways to approach this. So we have f of x is equal to x cubed. And we are looking for the derivative at x equals 1. What does that mean? It means find the slope of the curve when x equals 1. So essentially, this is the question. We're looking for f prime of 1. That's the question there, okay? Now, how do I find the derivative? Well, I take the limit as h approaches 0 of f of x plus h minus f of x all over h. This is option 1, okay? Now, we want to know at 1, so let's go ahead and go through that work. F of 1 plus h, right, because we're plugging 1 into the x, is going to be 1 plus h cubed. And then f of 1 is going to be 1 cubed, which is 1, okay? So we have our second coordinate, f of 1. Now we need to figure out what this is. Let me go ahead and change this. So instead of x, we're going to put the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. All right? And then from here, we can expand this out. If you guys are familiar with your Pascal's triangle, Pascal's triangle helps us deal with polynomial functions and expanding them. And I'm not going to explain all of this if you don't see it, but you can see if this was a squared. Uh-oh, my lights went out. There we go. Okay. If this was a squared, then this would say, let me flop these. It'd be h plus 1 squared, let's say. We know that this is h squared plus 2h plus 1. We can see the coefficients of 1, 2, 1. That's where this comes from, 1, 2, 1. When we cube it like we did, then we end up with this row. And the next row would be in Pascal's triangle, this one. Okay? But we're looking at this guy for a cube. So this is going to be h cubed because the coefficient's 1 plus 3h squared plus 3h plus 1. Now, I don't want to get into big, long details about that if you don't see that. And you probably don't see it right away. You probably haven't been exposed to it completely. If you don't see that, then just expand it. 1 plus h times 1 plus h times 1 plus h and simplify it. But the bottom line is this is h squared plus 3h plus, 3h squared plus 3h plus 1. Okay? All right. So we can plug those values into our difference quotients. Limit as h approaches 0 of f of 1 plus h. Oh, I have that wrong. That should say h cubed, 3h squared. I had that backwards. Okay, plus 3h plus 1. So that's this first part. And then minus f of 1, which is 1. And then all over h. We'll simplify that a little bit. And so we end up with those 1s are going to reduce. And we get h cubed plus 3h squared plus 3h all over h. We can factor out the h. So limit as h approaches 0 of h times h squared plus 3h plus 3 all over h. As a result of that, we can see that the h's reduce. And because they reduce, we can now plug in 0. And so we end up with 0 squared plus 3 times 0 plus 3, which is 3. And so we can say, I should probably write this in here, okay? This is going to be f prime of 1. And so f prime of 1 is equal to 3, or the derivative is equal to 3. So that's one definition that we can use. I'm going to go ahead and erase this part right here so that I can share with you the other definition, okay? All right, now, looks like that marker is going to die, so I'll just change colors here. The other definition said f prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So let's go ahead and figure out what each of these things are. Well, first of all, we want f prime of 1. Well, that implies that a is 1. So let's do that work off to the side there. We're going to say that f of 1 is equal to 1 cubed. And then, so that's going to go here. F of x, we're just going to replace the function f of x. So we end up with the limit as x approaches a of x cubed minus 1, because f of 1 is 1, all over x minus 1. All right? And so there we have our function that we just have to simplify. Sorry, it's x approaches 1 here, right? So what we need to do now is factor this guy and see if we can reduce that. Because if we plug in 1 now, we're going to get 0 over 0. So when I go to factor it, this is, you might be familiar with factoring this, but what I'm going to do is expand it so it's x cubed plus 0x squared plus 0x minus 1 for those that don't see it. And then I'm going to divide it by x minus 1. So I'm going to factor out of x minus 1 because I know that has to reduce somehow. And I'll do long division on this. So this is going to say x squared. That'll say x cubed minus x squared. And we'll subtract that. So we end up with positive x squared plus 0x. X goes into x squared 1x times. Multiply that. That's x squared minus 1x. We will subtract that. That becomes positive 1x, subtract the 1. And so how many times does x go into x? We got it once. Multiply that out. We got x minus 1. So we have a remainder of 0. So those are my two factors, at least. And so I can say that this factors to x minus 1 times x squared plus x plus 1 all over x minus 1. I'm going to get rid of this work here, but it's just a matter of long division there. If you don't remember how to factor that, we can see that the x minus 1's reduce. Okay, and so we have the limit as x approaches 1 of x squared plus x plus 1. We'll plug in the 1, so we got 1 squared plus 1 plus 1, which is 3. So f prime of 1 is 3. So there's two different ways of looking at it, and it's not a matter necessarily that you get to pick which one you like the best. It's a matter of you need to be comfortable with both of them because you see them represented both ways. Now I will tell you that this is the more traditional way of seeing it. This is a little less traditional. Sometimes this is way, way easier though. It just depends on the function, honestly, that we're dealing with. And so again, looking at our traditional definition, we're plugging in 1 plus h into the function, and we end up with this. We plug in 1 to the function, we end up with that. We combine like terms, and then we go ahead and factor the h out, and then we can see that the h is reduced. Then we can plug in 0, and we end up with 3 as a result. So the alternate method, as x approaches a, f prime of 1 is the limit as x approaches 1 of x cubed minus 1 cubed, essentially. I just plug those in into the difference quotient instead of over here. And then we can go ahead and factor the x cubed minus 1. We can say the x minus 1 factors out, those reduce, and then we can plug in 1 to our x's and get 3. So again, two different ways of looking at it. Let's go ahead and look at a practice problem here. I want you to go ahead and try and figure this guy out. This one's going to be kind of fun. I want you to try both methods, and see what you come up with. And when you're stuck or you're ready to see how you did, see if you got it right, go ahead and push play and watch the video. So in this one, it says let f of x equal radical x. F of x equals radical x. And I know some of you thinking, Bunye, come on, man, you just did the easy one. You gave yourself a polynomial, and here we got a radical. Why do you always take the easy problems? Because they just look easy when I do them. Doesn't mean that they are easy. Anyways, we are looking for the derivative of f at x equals 3. So essentially, we are looking for f prime of 3. That's the question, okay? So the original way of doing it, or the traditional way, it's the limit. Let me be a little bit more clear. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And then because I want f prime of 3, I'm going to go ahead and plug in 3 to my x values here. So this becomes f of 3 plus h minus f of 3 all over h. Now I'm going to skip the steps of figuring out what f of 3 plus h is off to the side, and I'm going to go directly into putting them into my equation here. So I got the limit as h approaches 0. Well, what is f of 3 plus h? That means I'm plugging 3 plus h into x here. And so this becomes radical 3 plus h. We're just replacing the x. What is f of 3 minus f of 3? That would be radical 3. And then all over, sorry, that should say h right there, all over h. You go, well, I don't know how to do that. Well, first of all, try substitution. Plug in 0. We're going to end up with 0 over 0. It's indeterminate. Now, what strategy have we used in the past to deal with this kind of limit? You could try factoring. Factoring is not going to work in this case, but you should be familiar with the idea that this is going to be a result of a conjugate. So I'm going to go ahead and multiply this guy by rad 3 plus h plus rad 3 over rad 3 plus h plus rad 3. And then see what we get here. So we end up with the limit as h approaches 0, and then distributing the top and everything, we're going to end up with just 3 plus h because the radicals go away. Those are difference of squares essentially, so that's going to be minus 3. And then over h times radical 3 plus h plus radical 3. Now from here, we see the 3 minus 3 cancels out or reduces each other. So we got limit as h approaches 0 of h over h times radical 3 plus h plus radical 3. And ho-ho, look at that. The h's reduce. You're left with the 1 on top. And now I can plug in 0 there. So we have 1 over radical 3 plus 0 plus rad 3. And that is, as a result, 1 over 2 radical 3. 1 over 2 radical 3. Okay? And so that is f prime of 3. Now, some of you might be saying, number one, do I have to rationalize that? And in calculus, we don't need to simplify anything. And rationalizing this, even though it would be a good practice, you would get rad 3 over 6. You don't need to do that because there's nothing to combine there. Others might be saying, oh, whoa, I saw that earlier. I remember doing this exact thing from the past, right? Just a couple weeks ago. And you're right. One thing that you've got to understand about calculus is that it all intertwines. The things that you learned a week ago are going to follow throughout the entire year. The things that you learn now are going to go through the entire year, and then they're actually going to rewind and go back into the things that you learned before. So the really cool thing about calculus is it ties all of the mathematics together, and it helps us understand it in a very intricate way. The problem is, for some of you guys, is you have this mindset of, I'll learn it for the moment, and then I'll forget about it after the test and learn whatever else he's going to teach in the future. It doesn't work that way. If you forget about it, you're going to put yourself in a position of failure in future lessons. So I don't want that to be the case. So make sure you're understanding these things as you go. Now, let's go ahead and look at the alternate way of doing this, the alternate way, and see what we come up with. Well, to figure out f prime of a, we take the limit as x approaches a of f of x minus f of a all over x minus a. And we are looking for f prime of 3. That means we are replacing the a value with 3. So that says the limit as x approaches 3 of f of x minus f of 3, because a is 3, over x minus 3. And so we got to figure this out. We got to figure out what these values are. And so we'll go ahead and continue on our journey through this problem. And we know that the answer should be 1 over 2 rad 3, or 3 over 6, rad 3 over 6. But what is f of x? F of x is radical x. F of 3 is radical 3, and then over x minus 3. So if we can figure out this guy, we should have the answer. And if you look at the steps here, the steps are essentially the same. You got a step for a step, basically. But here, notice what I was multiplying by. I was multiplying by rad 3 plus h plus rad 3 on top and bottom. This one's going to be a lot easier in terms of the conjugate. We're going to multiply this guy by rad x plus rad 3 over rad x plus rad 3, right? Because we're going to be multiplying by the conjugate of the numerator. And then that's going to simplify. That's just going to simplify to x minus 3 on top over x minus 3 times rad x plus rad 3 on the bottom. And then you can see the x minus 3 and the x minus 3 both reduce each other. We're left with 1 on top, and then we can plug in our 3 value. So we get 1 over radical 3 plus radical 3, which is equal to 1 over 2 rad 3. And we have the same answer. So you can see the level of work involved. There was a lot more work on this side than this side. Even though the work was very similar, it's a simpler function or a simpler expression to be working with than this one is. Either way works, but I want you to feel comfortable with both ways. All right, so just a quick recap. The first way, we are plugging in 3 plus h into our f of x function and putting that here. We're plugging in 3 to our f of x function and putting that there. And then we're doing the conjugate thing, simplifying that, plugging in 0 to our limit expression. Now, I do want to point this out because some students make a mistake on this. Because we are looking for f prime of 3, students will tend to want to plug in 3 down here on this step. Well, okay, we want f prime of 3, so we're going to plug in 3. No, f prime of 3 is equal to this expression, and we're not taking the limit as something is approaching 3. We're taking the limit as h approaches 0. So we're plugging 0 into h there. Okay? So the second part, again, you got f of x minus f of a over x minus a, and then f of x is just rad x, f of 3 is just rad 3. We do the conjugate thing again, and then we end up with those reducing, and then we're plugging in this case, we are plugging in 3 to x because we're taking the limit as x approaches 3, whereas here h approaches 0. So not to be confused amongst those two. Okay? All right, the next slide. Some of you guys asked me about this idea earlier. Do we have to plug in 3? Do we have to plug in 3? Could I just leave it as x and work through that and then plug in 3 later? The answer is yes, but I didn't want to get to that point until right now because I wanted to define what you were actually doing when you did that, okay? So, the derivative as a function, what I have defined for you so far is the derivative at a point. So if I look at the curve and I say, what is the derivative at that point? It means I'm finding the slope of the tangent line at that point. But we know that as I move that point around, the slope of the tangent line is changing, or the slope of the curve is changing. So what we do to represent all slopes, not just the slope at this point, instead of looking at something like f prime of 3, we just say something a little bit more in general. We would say, what is f prime of x? And so that will tell me, that will be a function that represents the slope of the curve at any x value. All I have to do is plug in the x value to figure that out, okay? So that's the difference between the two. This is a function where this is the derivative function that represents all slopes. This is the derivative at a singular point on the curve. Okay? This is a numeric value and this is a function. All right, so with that said, let's go ahead and take a look at an example of this. It says, what is the derivative function of f of x equals 3x squared? Well, f of x equals 3x squared. All right, we've got that. We are looking for the derivative function. So we are asking for what is f prime of x now? Not f prime at a point, f prime of x, which means a function that represents all slopes. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? This is where your algebra skills really got to be good. If you're making arithmetic errors or plugging things in wrong, it's not going to work out very well for you. So f of x plus h means we're plugging in x plus h. So we're not plugging in a specific number for x right now. We're keeping it in general. We're going to plug in x plus h in place of x here. So this is going to say 3 times x plus h squared. 3 something squared. F of x is 3 something squared. We wanted f of x plus h, so it's 3x plus h squared. Minus, what's f of x? Well, f of x is just 3x squared all over h. Okay? And so we will figure this out if we can simplify this. So the first thing I'm going to do is I'm going to multiply I'm going to square that binomial there. I'll keep that 3 out front. That'll be x squared plus 2xh plus h squared. And then minus 3x squared out back, all over h. And then distributing the 3, we got 3x squared plus 6xh plus 3h squared minus 3x squared all over h. And then from here, we can see that the 3x squareds reduce. So we got the limit as h approaches 0 of 6xh plus 3h squared over h. We can factor out the h. So that becomes 6x plus 3h all over h. We can see that those h's now reduce. And we can plug in the 0 to the h, so that would be 3 times 0 is 0. So our final answer is just 6x. So we can now say f prime of x is equal to 6x. Okay, now if I were to ask you what is the slope of the curve when x equals 2, then I would be asking for f prime of 2. I could go back and plug in 2 here and evaluate it all the way through, or now I can just plug in 2 there. F prime of 2 is just going to be 6 times 2 because this is the f prime function, which is 12. And now watch what happens. This is 3x squared. So we know that the parabola is a vertex of 0, 0. It's pretty steep, right? But watch this. This is kind of cool because you can verify these things. What would you say the slope should be at x equals 0? What kind of line would that be? Well, that would be a horizontal tangent line, right? That's how the tangent line would be because it's the vertex at the bottom point. So let's figure it out. What is f prime of 0? F prime of 0, the derivative when x equals 0, is equal to 6 times 0, which is 0. What's the slope of that line? The slope of the line is 0. Now, if I were to look at, let's say, 1, at x equals 1, and draw that tangent line, f prime of 1 is equal to 6 times 1, which is 6. So the slope of that line should be 6 if I had a perfect graph. And we already know that f prime of 2 is, sorry, that should say 12. F prime of 2 is 12. So if I move over to 2, we can see a tangent line that's even steeper. And so as we move further to the right, we can see steeper and steeper, or bigger and bigger numbers, which means the slopes are steeper. This, again, remember, is slope. What's the slope of the tangent line when x equals 0? What's the slope of the tangent line when x equals 1? And so on and so forth. So you can see getting the derivative function helps us evaluate all the different points a lot faster than plugging each of those individual points, plugging in 0 there and evaluating, plugging in 1 there and evaluating, and so on. We can deal with the function instead, and that just makes our life easier. All right, so again, not plugging in a number at this point, we're just leaving it in terms of x. And then go ahead and expand that, distribute everything out, make sure I got it all good, looks good to me. We're going to go ahead and cancel those things out, factor out the h. The h is reduced, plug in 0 for h, and we end up with 6x is f prime of x. And so that's how we approach it. And again, I can make it easier now to figure out the slope when x equals -1, because all I have to do is plug in -1 to the derivative function instead of going through this whole process again. So we end up with a -6 slope. And you can see if I go back 1, the slope of the tangent line there would be a negative slope. It's going downhill. Okay. Now, one more thing on this, we can now ask, because this is going to cycle back through more questions, what is the equation of the tangent line of f of x when x equals -1? So the tangent line, remember, to create a tangent line, go back to way back to Math 1, Math 2. We've done a ton of creating lines. We need two things. We need a point and we need a slope. Well, we know the slope at f prime of 1, so we'd say f prime of 1 is the slope. Sorry, f prime of -1. So that would be 6 times -1, which is -6. And then the point would be we need to plug in -1 to the original function. So what is f of -1? Well, that'd be 3 times -1 squared, which is 3. And so now I have my point and my slope. So this is going to say y minus 3 equals -6 times x plus 1. And that is the equation of my tangent line. If I wanted the equation of the normal line, well, we know the point is still the same. The slope is going to be the opposite reciprocal, so that'd be 1/6. So then our answer would be y minus 3 equals 1/6 times x plus 1. And then that is that. Okay? And so you can kind of see how all of that ties together a little bit more now. And if I were to graph that line, we would see a tangent line and a normal line going through that point. Okay? You guys go ahead and try this problem, see what you do, see what you come up with. I am looking for the derivative function of g of x, which is 1 over x. And then I want you to find the equation of the normal line to g when x equals 5. So go ahead and pause it and then come back and see how you did. All right. For the derivative of g, we know that g of x is equal to 1 over x. Okay? And we are looking for the derivative function. So we are looking for g prime of x. And so we'll plug that into our difference quotient, limit as h approaches 0, of g of x plus h minus g of x all over h. And then we'll go ahead and plug x plus h in. So we got limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. Now, how do we deal with this kind of guy? If I plug in 0 for h right now, I'm going to get a 0 over 0. So I have to do something algebraically here to fix this. Factoring isn't going to work. Conjugates isn't going to work. And this is what I talked about the other day. Any form of algebraic manipulation that makes this look different but still be equivalent should be sufficient. Okay? So what I'm going to notice is that in the numerator, I am subtracting fractions. So in order to subtract fractions, I need to get a common denominator. So I'm going to multiply the first guy by x over x, and I'm going to multiply the second guy by x plus h over x plus h. And then we're going to go ahead and figure that out. So we got x on top there over x times x plus h minus x plus h over x times x plus h. And you could simplify all that out, but I'm going to leave it like that, all over h. Okay? Now, since those have a common denominator, we can put those together. So that's a limit as h approaches 0 of, when I subtract that, remember, this is in parentheses, so we have to distribute that negative. So it becomes x minus x, which is 0, and then a negative h. So we end up with negative h over x times x plus h all over h. And then simplifying this, we talked about this the other day in a previous video, so I don't want to dwell on this, but the h on top and the h on the bottom will simplify. That'll be negative 1 over x times x plus h. And then when I plug in 0, I end up with, for h, plugging 0 in for h, I end up with negative 1 over x times x plus 0, or x squared. So we can say f prime of x, sorry, not f prime, g prime of x, g prime of x is equal to negative 1 over x squared. All right, so that is my derivative function. Now I want to find the equation of the normal line when x equals 5. So the first thing I have to do is figure out what g prime of 5 is. So that would be negative 1 over 5 squared, which is negative 1 over 25. That is our g prime of 5, right? Now, what does this mean again? What does the derivative mean? It means the slope of the tangent line. We want the slope of the normal line, so I'll write it like this. Slope of normal line would then be the opposite reciprocal, so it would be positive 25. And then we also need our points, and our point was when x equals 5, so we're going to plug that into our g function. So that'd be g of 5, which equals 1 over 5. And so our equation for our normal line, okay, normal line, is going to be y minus 1/5 equals 25 times x minus 5. And there you go. Again, no need to simplify that. Leave it in point slope form. All right, going through the process again, just trying to simplify that by getting a common denominator here, not plugging in a number here, just using terms of x to get the derivative function, and then simplifying those h's, so we end up with negative 1 over x squared plus xh. I did on here, but same thing there. And then plugging 0 in there, we end up with negative 1 over x squared. And then plugging in 5 to find the slope of the tangent line. And then to find the slope of the normal line, we flip and switch opposite reciprocals, and then plug that into our point slope form, and we have our answer. All right, last problem here. It's an exit problem. I want you to just figure out what f prime of x is given that function. Go ahead and pause it, see how you did after you're done. So for this problem, we have f of x equals 2/3 x cubed. Okay, now I'm not going to spend a whole long time on this, but you can check your work because I'm just going to give you your answer. F prime of x is then going to be 2x squared. Okay, so that is our final answer there. Again, I'm not going to do that in front of you. If you want to go through this and then ask me for help afterwards, you can. I just figured this video was kind of long enough. And with that said, that wraps up this lesson on what the derivative is. The derivative is the biggest piece of calculus. We're going to learn how to simplify the process of the derivative. We're going to learn the application of the derivative. We're going to learn how to go this way with the derivative, and then we're going to learn how to go back that way to get back to the derivative. And that's the whole encompassing concept of calculus, is what the derivative is going forwards and backwards and all around. So we have just introduced this idea, this very important idea that we're going to be repeating over and over again throughout the year. With that said, if you have any questions, any comments, please do so in the comments below or reach out to me and I will do my best to help you. Otherwise, I will see you next time.